Welcome to our paper dataset distillation via Vision Language Category Prototype. Dataset distillation, DD, compresses large datasets into compact yet informative surrogates, preserving performance while reducing storage, data transfer, and computational cost. However, prior DD largely distills from images alone and overlooks semantic context. This weakens generalization on complex data and can yield illogical outputs or missing targets. As shown in the figure, GR without text sometimes generates background-only images and anatomically implausible results, for example, dogs with 5 legs. A further issue is co-occurrence bias. Frequently paired elements, e.g., fish and green plants, dominate the surrogate data, so models overfit to their coexistence rather than accurately representing each component. These failure modes arise because current methods focus solely on visual features and neglect semantic signals. Lacking contextual guidance, the synthesis process cannot reliably produce coherent, target-containing images, which ultimately degrades the quality of the distilled dataset. The contributions of this study are summarized as follows. To the best of our knowledge, this is the first work that integrates language information into visual dataset distillation for classification tasks. We employ open-source large language models in DD to generate descriptive text for unimodal data, addressing the lack of textual descriptions in existing DD benchmarks and improving the generalization of our method. We propose a novel text prototype scheme for DD, which leverages word frequency within each cluster to ensure the representativeness and diversity of the text prototypes. Next is the overview of the proposed framework. The framework starts with generating image-text pairs using the LLaVIA model, followed by training a diffusion model. Image features are then compressed with an autoencoder, outliers are removed, and k-means clustering is applied to create image prototypes. For text prototypes, frequent words are extracted from descriptions, and the most representative sentence is selected. Finally, these prototypes guide the diffusion model to synthesize diverse and representative images. On ImageWoof, we evaluate under varying IPC settings using 3 backbones: SON-VNet 6, ResNet AP10, and ResNet 18. Across all settings and models, our method consistently outperforms the second-best approach, demonstrating robustness and adaptability. Notably, at IPC equals 10 with ResNet 18, we achieve 39.9% top 1 accuracy, plus 2.6 points over the second best. These gains persist for SON-VNet 6 and ResNet AP10, indicating that the approach generalizes across architectures and IPC regimes, rather than relying on a particular model capacity or bias. We assess our method on ImageNet and ImageIDC using the ResNet AP10 architecture under IPC 10, 20, and 50. The results show that our method consistently outperforms all other approaches across varying IPC settings on both datasets. On the ImageNet dataset, our method significantly surpasses other methods, achieving a 4.1% improvement in average accuracy. We conduct experiments on ImageNet 1K under IPC 10 and IPC 50. The results indicate that our method consistently outperforms the others, achieving superior performance on large-scale datasets. We also evaluate our method on 2 low-resolution datasets, SAFAR 10 and SAFAR 100, both with a resolution of 32 by 32. As shown in the table, our method surpasses SRE2L and RDED across different IPC settings on both datasets. Notably, on SAFAR 100 at IPC equals 10, our method achieves a significant 8.0% improvement over RDED. Our approach is especially effective for complex datasets like SAFAR 100, showcasing its robustness across datasets with various resolutions and complexities. Following KRRST, we evaluate transfer learning using ImageNet 1K distilled data, IPC equals 10 shown in table. Our method outperforms KRRST across all datasets, with a notable 5.9% improvement on flowers. For ImageNet, models trained on D4M distilled data often focus on background due to co-occurrence bias. In contrast, our synthetic data encourages attention to target objects, e.g., fish, parachute. Cluster-specific text guidance enhances background diversity and promotes object-focused generation. The text prototype provides insights into the linguistic patterns associated with different clusters, highlighting both representative and non-representative NR characteristics, as shown in table. In the Saluki Gazellehound class, non-representative words appear in more than 70% of the samples, including the class name itself and its common characteristics. For example, white, long, and slender are classified as non-representative words since they describe fundamental characteristics of the class. A slender dog with a long body and a coat that includes white. As these characteristics are prevalent across multiple clusters, they are unlikely to characterize individual clusters. Feature keywords are selected on the basis of their frequency, which serves as an important score. In the feature keywords of Cluster 3 in Table 6, we observe that 112 out of 166 samples describe a grassy background, 112 mention a large target size, 96 feature the color brown, and 72 depict the action running. This indicates that nearly half of the brown dogs are running on the grass, which is consistent with the generated images. It also enhances logical consistency, such as dogs with 4 legs rather than the 5 legs seen in the label-only images. To evaluate the quality of the synthesized images, we compare samples generated using the same image prototype, corresponding to each column, across different semantic strategies, as illustrated in the Fig. In the Saluki case, L plus FK, and GGS generate images with severe flaws, such as extra or missing limbs, while DCS consistently generates a logically coherent Saluki with the correct number of legs. Additionally, in the 4th column, only DCS successfully synthesizes images containing the target object, while the other methods fail to do so. Although L plus FK contains more features than L, these words are unordered and unstructured, and they lack logical relationships, leading to misinterpretations. GGS generates sentences based on FK not encountered during the model's training, which may fail to provide the necessary context for accurate object generation. In contrast, DCS offers more detailed and context-rich descriptions, ensuring that the target object is consistently included in the generated image with all relevant features. First, we introduce the first dataset distillation framework that jointly leverages image and text prototypes. Second, we employ open-source LLMs to generate descriptions for unimodal datasets, addressing the lack of textual labels and improving generalization. Third, the resulting images are more coherent, with clear target objects and realistic backgrounds. Finally, across multiple benchmarks, our method achieves state-of-the-art accuracy, underscoring the value of multimodal guidance. Thank you for your attention.